Okay guys, on this video we're going to be talking about oxidation rules. We have looked at this before. If you remember at the beginning of the year when we got our periodic tables, I had you guys write these numbers above these charts. And well, if you remember what these oxidations represented, it was how much things wanted electrons. So they would freely give them away, or some really wanted electrons. And if you remember, the outsides of the charts, they were the more extremes, and they were the ones that either really wanted to get rid of them or really wanted to have them. And so if I zoom in on this chart a little bit, okay, we wrote +1s for all of the alkali metals, and then the alkaline earth metals were 2. This center spot, they were kind of all over the place, right? And we're going to see that when these things make compounds, we can start to kind of piece together what their charges might be, okay? And over here on the right hand side, we had the different groups and those charges. So we're going to now take a look at some rules that have to do with these different charges. Okay, so these are the rules that we've kind of abbreviated for assigning oxidation numbers for these things. So rule number 1, pure elements are 0, so their oxidation number is 0. So if you had an oxygen molecule, it would just be 0. Number 2, all monoatomic ions are their usual charges. So these are things that we would see by themselves, or typical +2 or +1 charge. Number 3, all neutral compounds must have a net charge that equals 0. So when we put compounds together, you remember that their overall charge is 0. That's what that's talking about. And number 4, all polyatomic ions must have a net charge that matches their usual charge. And so if you remember, off the back of our periodic table, we have these polyatomic ions down here. Their net charges must be, in this column we have -2 charges, they must be -2, even though they're a polyatomic ion. So there's different things, and really this is best me showing you on some practice problems and examples. So also, before I forget, you may want to screenshot this, and you have this as a reference for you. Take a picture with your phone so that you guys can have this as a reference when you're working through some of these practice problems. Okay, if we take a look at the rules, I've just kind of written a simplified version of this. Your homework is going to look something like this, okay? We just give you the names of compounds, and you have to identify what the charges are for each of the elements that are written there. So we need to assign oxidation numbers to each of the elements. So first of all, we need to write these things correctly. So if we focus on potassium permanganate, okay, this is going to be potassium's a K, permanganate, if you look off your polyatomic side of your chart, is MnO4. Okay, so if we go back to our rules, okay, we always want to kind of start with our extremes. Okay, so our ions here at the edges, so that's what I mean by starting at the edges or extremes. Oxygen is a -2 charge, but how many do I have? I have 4 of those. Okay, so 2 times 4 is 8, so this is going to be a -8 charge. Okay, potassium is a +1 charge. I have 1 of them, so this is going to represent a +1 charge. So what has to go here? If I go to my rules, it's a neutral compound, so this must equal 0, okay? So if this has to equal 0, what number does this have to be for this to work out here, okay? So obviously that's a +7, and so we kind of work backwards. There's only one manganese here, so it represents a +7. And so I believe on your homework it says it has each element written out. And so these are the numbers that represent the oxidation numbers for all of those elements. So potassium's a +1, manganese represents a +7 here, and oxygen represents a -2. Okay, so all right, we're going on to our next one here. Magnesium nitrate. Okay, So magnesium nitrate, NO3. Magnesium, you should know, is a +2 charge, so I need 2 of those things, okay? So this one is a little bit trickier, but I always start at the edges again. Magnesium off of the chart, okay, off of our periodic table off the front like we've always done. It's a +2. I have one of them, so it is going to play a +2 charge, okay? Oxygen is always a -2, but how many do I have here? Well, I have 6, okay? So 6 times 2, that's gonna be a -12, and this has to add up to 0 again. So what number has to go here mathematically to make this statement true? Okay, that has to be a +10. But now working backwards this way, how many nitrogens do I have? I have 2, so 10 divided by 2 is 5. So nitrogen is playing a +5 on this. Okay, so to clean this up, we're going to have magnesium is going to be a +2. Nitrogen is a, these are my answers here, +5. And oxygen is going to have a role of a -2 charge. Okay, so again, this is all going to show later on when we see how these compounds go together, whether something has an affinity to give off, lose electrons, or if something is going to gain electrons. And so we need to know what these numbers represent here for each of those atoms to figure that out. Okay, so let's go to sulfuric acid. Sulfuric acid is our next one. Okay, so if you remember off of our chart, it's H2SO4. Okay, if I take a look at the rules here, right, this is a neutral compound again, so this is going to add up to 0. What do I mean by that? There's no charge. It's not an ionic compound. Okay, so hydrogen off of our chart is a +1. How many do we have? 2. So that is a +2. Oxygen is always a -2. How many do I have? 4. So that is going to be a -8. So this is going to be a 0 net charge again. So what number has to go here to make this mathematical equation correct? That has to be a +6 to make 0. So sulfur is, in this instant, is a +6. And if you remember off of our oxidation chart, it's not a +6, okay? It's a -2 charge. And so so this is showing that when these things combine in compounds, their roles are going to switch, and those oxidation numbers off of the chart are not necessarily going to be true. Okay, a couple more here. Aluminum sulfate. Okay, aluminum sulfate is Al2SO4 3. So we still write these things as if the charges above them still crisscross and count. Okay, but now I'm going to keep track of how many that we have here. Okay, and so oxygen. Okay, oxygen is a -2. How many do I have here? Well, I have 12. If I have 12 -2s, that's going to be a -24. Holy cow. Okay, aluminum. Aluminum off of our chart is always a +3. Okay, and so this is going to be a +6 charge. So what mathematically has to go here to make this 0? Well, it has to be a +18. Okay, a +18. Well, how many sulfurs do I have? I have 3 of those. So 3 divided by 18 is a +6. So again, to show you, to write this out, we're going to have, just to clean it up, aluminum is going to be these are my answers here. Aluminum is a +3, sulfur is a +6, and oxygen is a -2. Okay, so those are the rules that they take. Okay, and I forgot to write that up here. You guys will clean that up on your homework for us. I think we even have spaces for you to write that.
Okay, a phosphate ion here. Now, well, the rules are changed here a little bit, okay? If you take a look at this, okay, I have, it's a polyatomic ion because there's more, phosphate means that there's more than one atom by itself, okay? So it needs to be the same off of our chart. And so if you look up phosphate off of our chart, it has a -3 charge, okay? So this is going to be PO4 with a -3 charge. So instead of writing this as 0, these numbers need to add up to a -3. So in this instant, we know what oxygen is going to be, because like we've said before, oxygen is usually, almost always, and we're just going to say always, a -2 charge. So that means it's going to be a -8. So for this mathematical statement to be true, what does this number need to be? Well, it needs to be a +5. Okay, because if I add those together, that would give me a -3. Now working backwards just to make sure, there's only one phosphorus, and so that is a +5. And so those are my answers. Phosphorus in this example is a +5, and oxygen is a -2. Okay? The one thing we haven't, that I didn't really show you, is if we had a pure element. So let's say we had something like oxygen, okay, by itself. It is a pure element, so its oxidation number value would be 0, okay? And then all of our monoatomic ions, they're their usual plus or minus charge. And what does that mean? If I had chlorine by itself, okay, it would be its -1 charge. If I had calcium by itself, it would be its +2. Okay, so these would be the typical values if these things are by themselves. So that's what that prefix mono means. So that kind of goes over the rules.